So yesterday we went in depth into how to do vector component addition. Okay, and that is where we draw our multiple angled vectors, tail to head, okay, turn them into right angle triangles where we can calculate their horizontal and vertical or x and y components, okay, where we take those x and y components to find our resultant and move on from there. Okay? How many people are finding the diagrams to be pretty straightforward? Okay. We do always show something to people like on kind of the second or third day of doing vector addition, just in case you're finding the diagrams to be really like busy and distracting. Okay, because for some people, like having all these triangles and all these lines overlapping just kind of becomes overwhelming. Okay, and if that applies to you, that's fine. Okay, I want to show you how you can draw the diagram a little differently that might make it a bit easier. Right now, there's one drawback to that method, and that is that you can't see the final product until you're ready to draw it. So that may not make sense until I show you how this works. Okay, so what I want you to do right now, guys, is to get the diagram drawn for number 2 here. And I'm going to solve number 2 using what we call the separate triangle method, which is the other method I was just talking about. All right, so if you guys can get going and get a diagram drawn for number 2, okay, I'm going to show you what the diagram using the separate triangle method would look like for number 2, and then you can decide which method is for you. Okay, so I'm first going to draw this the way we learned how to draw it yesterday, drawing the tail to head, so you can kind of see what that looks like. So my first vector is 15 meters at 15 degrees north of east. So I'm going to draw myself a reference line that is east. I'm going to have a pretty shallow triangle because 15 degrees is not a very big angle. Okay, 15 meters long, and have x and y. And I'm drawing it really small because I'm going to show you the other method in more detail on this question, just for reference. Okay, and then my other vector is 13 meters long at 5 degrees west of north. So again, a really narrow triangle, probably even narrower than that, but this is really small and getting crazy already. Okay, so this would be y, this would be x, and this side here would be the 13 meters, and that would mean that my resultant goes like this and would have a triangle that looks like that. This would be my total displacement, y and x. Okay, so the advantage of the tail to head method is that I can see the big picture. Once I have it drawn, I know where I'm headed. I can kind of check my answers with my diagram as I go along. That's its advantage. Its disadvantage is it gets busy. It gets crowded. It gets maybe sometimes hard to read and confusing. All right? The other method we call the separate triangle method. It's exactly what it sounds like. We don't draw them tail to head. We just draw separate triangles. All right? So my first one, I would just have 15 degrees, 15 meters, x and y, and then I'd have my other one, okay, which would be north, okay, 13 meters, 5 degrees, x and y, right? I'm still going to get all the same numbers for black x and red x and black y and red y. I'm going to get all the same numbers because the triangles are the same. The advantage of this is scale is meaningless. Okay? I can draw these triangles whatever sizes I want because they're not attached to each other. Okay? And it never gets busy. The disadvantage is I can't see where I'm going. Okay? I don't know what my final resultant should look like until I've done all the calculating and I build it from the numbers. Okay? With the first method, I build it from the picture. With the second method, I build it from the numbers instead, so it's not there until I'm on the last step. Right? It's less crowded, it's less confusing, but you don't see what you're headed towards till the end. Okay? So the rest of this is the same, regardless of which method you choose. Right? The first thing you got to do is find all your x's and y's. All right? So black x is adjacent, so that'll be the cos of 15 times 15. Black y will be the sine of 15 times 15. Okay, so angle times hypotenuse. Okay, so 14.49 we'll say. Alright, 3.88. And then for the red one, so red X on this one is, is adjacent. So it's the cos of 5 degrees. Sorry, I'm just making a huge mess here. No, it's not. I was right before. It's the opposite side. More coffee, please. Sine of 5 times 13. And y will be the cos of 5 times 15. It's because I did this wrong. That's why. That's x. It's so small I can't even read my own writing. Okay. Sine of 5 times 13 is 1.13. And that is east. Sorry, that's west. West. Okay, and then cos of 15, cos of 5 times 13. 12.95. That's north. Okay, so regardless of which method I use, I still have to calculate all the x and y components. That part doesn't change. Neither does the next step. If I'm going to find my resultant triangle, I've got to find its x and y's by adding together the x's and y's that I just calculated. Is that ringing a bell from yesterday? Yeah? Okay. So to get green x, okay, I'm going to add 14.49 plus negative 1.13 because that one's west, right? The 1.13 is west. Okay, so we're looking at 13.36 meters east. Okay, and then for y, they're both north, so I just have to add them, so that'll be 3.88 plus 12.95. Okay, so we're looking at 16.83 for that one. Meters north. All right, now there's going to be a difference. With my first method, the tail to head method, I can now look at those numbers, look at my drawing and go, yep, that looks pretty good. Okay, my diagram and my numbers seem to agree for the most part, so I probably drew that reasonably well. With the separate triangle method, I now have to build my resultant. Okay, so now I'm going to draw the resultant's triangle using the two numbers I just calculated. So my x is 13.36 meters east. Okay, and that will be x. And then the y will be 16.83. So I didn't leave myself quite enough room here. Okay, so now I've got that built, okay, and now I can draw my result. Okay, and it looks pretty much the same as the other triangle that I got using the tail to head method. It should, it's got the same sides. Okay, now all I have to do is find the angle. Now, I think on the one I drew, I actually drew it the other way, and that's fine. Okay, I could have also drawn it this way, so I could have gone got it that way. Still going to be the same regardless. Everyone okay with that? Okay. All right. So now I've got the sides. Now everything else is the same. I have my final triangle, I do Pythagorean theorem to get D, I do trigonometry to get theta, I get the same answer regardless of which method I use. All right, so to get what D is, okay, it'll be 16.83 squared plus 13.36 squared. All right, so we're looking at 21.48, right? 21.48 meters, and then theta will be 10 to the minus 1 of 16 over 13. Whoops, I can't write it that way. I have all the decimals. All right, so 51.57 degrees. Okay, and that'll be north of east, so I think we only have 2 significant digits, so it's going to be 21 meters at 52 degrees north of east, or at 28 degrees east of north. Either one will be fine. Okay, everybody all right with that? If you were fine with the method we used yesterday, you can forget everything I just drew. Okay, but if you were looking for something less confusing, this is less confusing or less busy. Okay, whatever. If it was bothering you visually, the separate triangle method might be better. Okay, if you were totally okay with drawing them tail to head, keep drawing them tail to head. They both end up mathematically the same. Questions there? I want you to try number 3. Here's why I want you to try number 3. Scale matters. I want to illustrate the importance of scale matters with question number 3. All right, so I'll give you a few minutes to get the diagram drawn for number 3. So, while tracking a polar bear, a wildlife biologist travels 300 meters south and then turns and goes 550 meters at 75 degrees north of east. All right, so here's my reference line, east. And I'm going to go 75 degrees north of that. Okay, what I see a lot of people do on that diagram is they do this. Done, it's perfect, that was so easy, it got level with my first one. No chance. There's like 0 chance that that would happen. Okay, and think about your scale. This 550 meter line is almost twice as long as the 300 meter line. But people forget that when they get drawing this, especially when something backtracks. Okay, one went south, the other's going north, and when they backtrack, people tend to blow their scale out of proportion. Okay, we don't want to do that. We want to make sure that we reflect that scale, because when it backtracks is when scale is most important. Okay, if they're all going the same way, it's not as big a deal, but here it's crucial, because otherwise I'll get a weird resultant. Okay, when my resultant should go like this, and I might have actually drawn that a little bit too long. Now, if you recall, I told you that this is the kind of question I might put on a unit exam. That is exactly the kind of question that I might put on a unit exam. Okay? One of them is vertical, the other is angled, and it backtracks. So it makes you really keep track of scale and of your directions. Okay. All right, I'll give you a couple more minutes to get ahead of me there, and then we'll have a look at the solution to that one. Okay, let's have a look at the rest of this one. So, because the 300 meter vector is due south, its x is 0 meters because it doesn't go east or west. Okay, and its y component is 300 meters south. Right, so that one's easy, there's no calculating involved with that one. Okay, red x is adjacent to the 75-degree angle, so that'll be cos of 75 times 550. And so that's 142.35 meters east. And then my y component is the opposite, so the sine of 75 times 550. Okay, 531.26 meters north. All right, so now I've got all my x's and all my y's. Now I need to find my resultants x and my resultants y. My resultants x is easy because one of the x's is 0. Okay, so the overall red x and green x are equal. Okay, so that's going to be 142.35. That doesn't really require us to do any calculating. Meters east. Okay, green y, that does require us to do some calculating, and it requires us to recognize that one of those vectors is negative because it's south. All right, so what are we looking at? 231.26. Okay, meters north. Okay, everybody all right with that? My diagram's actually not looking too bad right now. The y on my green triangle is quite a bit longer than the x, so it's not too bad. Right. So now that I've got those, now I can calculate my overall displacement. Okay, so that'll be 142 squared plus 231 squared, obviously with all the decimals in place. Okay, so my overall resultant is 271.56 meters. Okay, and then I need to find theta. All right, the way I drew that, x is opposite, y is adjacent. So 10 to the minus 1 of 142 over 231. Okay, we'll give me an angle. All right, so we're looking at 31.6 degrees. And according to my triangle, that's going to be east of north. Okay, so that one only has 2 significant digits. Okay, so we're going to have 2.7 times 10 to the 2 meters at 32 degrees east of north, or at 58 degrees north of east. Okay. Are you all right with that one? Okay. I'm going to give you about a 5-minute break here before I throw a different one that scale is even more important. Okay, listen up here, guys. So this is going to be the trickiest one you've done. Not because the math is any harder than any of the ones you've done. It's not. It's still trigonometry. It's all that diagram that's tricky. Right? So this one's scale is really important. Everything backtracks, both x and y. They reverse themselves. So you have to be very, very careful about how you draw the diagram for this one. Right? Give you some time to get ahead of me here, get the diagram done, then we'll look at that, and I'll give you some more time to get ahead of me again. Okay, so we have first it going north of west, and then we have it going south of east. Okay, so it's like totally backtracking on itself. All right, so I'm going to start kind of here in the middle, and I'm going to go 950 meters north of west. Okay, so there's my reference line that's west. I'm going to go 30 degrees north of that. So this will be Y, this will be X, and this will be 950 meters. Okay, then our next one goes 385 meters at 45 degrees south of east. Okay, so here's where scale becomes important. My reference is east. The line I'm drawing is like 1/3 as long as the first one, okay? At least approximately. The angle is 45 degrees. Now, if I'm looking at this as a rectangle, if this angle is 30 degrees, what's this angle?
60.
Right. Okay, so my 45, well, actually this angle would be 60. This angle would be 30, right? Similar triangles here. Everybody okay with that? So that kind of can guide me as to where this next line should go. Should it go above this or below this line? A little bit below. Okay, so I'm going to draw that one kind of like this. And I didn't draw it very well. I made it way too long anyway, so try that again. You can't go west of east.
No, you said I read it as west.
Oh. Well, you can go west of east. You're going west if you do that. Okay, so now I've got that part drawn. Now my resultant needs to go from my initial position to my final position. Whoa, which hopefully is straighter than that. Okay, kind of like this. Okay, so that mess is what my diagram should look like. This is one of those ones where the separate triangle method might be a little more visually pleasing, and because you don't have lines going over everything. Okay, but I still like this method because I got to see the big picture. Okay. Now actually, you know what? I got to change this because I messed the length up. Remember how important I said scale was? I made this just way too long. I drew it the right direction, but I made it way too long. Should probably be more like there. All right, because I said it needs to be about 1/3. It certainly needs to be less than half, and where I drew that the first time, this is even probably a little long. Okay, I'll give you a few more minutes to get ahead of me. Okay, so now that we've got our busy diagram, okay, all drawn here, we got to find all the x's and all the y's. Okay, so we're going to go x, black x that is the cos of 30 times 950. So 822.72 meters west, okay, and y is going to be the sine of 30 times 950, which is going to be 475 meters north. Okay, everybody all right with that? All right, then I got to do the same thing for the green triangle. Okay, so green x is the adjacent side, and that's going to mean cos of 45 times, how long was that one? That was supposed to be 385 meters. Okay, times 385. Okay, so that's 272.24 meters, and that's going to be east. Now, if I'm paying attention, can I save myself some time here? 45 degrees cuts the rectangle in exactly half. Would you agree? So sine and cos of 45 just so happen to mathematically be the same number. Because if I have a 45-degree angle in my triangle, x and y are equal. Right? So I can save myself a little bit of time and just say that y is 272.24 meters south. Okay? Everybody okay with that? So now I can go about finding what my resultant's triangle looks like. Okay, so blue x is going to be 822.72 minus the eastern part, which was 272.24. All right, so 550.49. Meters west. And yeah, that's all right. It's a little longer than y, so far so good. Okay, and then for y, I'm going to have the 475 meters north minus the south, which was 272.24. Okay, 202.76. Meters north. All right, that really does fit pretty well. It's a good thing I redrew the triangle because it wasn't going to look that good, okay, the way I originally had it drawn. Okay, so now the scale is much better. And now I can calculate my overall displacement, Pythagorean theorem, like we always do. So 550 squared plus 202 squared. It gives me a magnitude, oh, not like that, it won't. That's better, 586.64 meters. And to get theta, right, the way I drew the triangle, y is opposite, so tan to the minus 1 of the 202 over the 550. Okay, will give me my angle. So we're looking at 20.2 degrees. That fits with the triangle I drew. And for me, that's going to be north of west. All right, we're looking back at our question here. My final answer should have how many significant digits? 2. All right, so we're looking at then 5.9 times 10 to the 2 meters at 20 degrees north of west, or at 70 degrees west of north if the triangle was drawn the other way. All right, like I said, that would be as tough as they would get. Most involved, okay? Diagrams most important. Tomorrow, we're going to take a little break from just doing vector component addition. We're going to start a little group thing that we'll do Friday and probably Monday, okay? That's using maps, okay? So we'll do a little bit of hang out with real people and do that kind of stuff. Okay, so that's what we'll be doing tomorrow on Monday. All right, if I can get everybody to mask up and clean off their desks, I'll wipe them down.